Assalamualaikum and good day everyone. Today, our group will present on the applications of ultrasound wave technology in scientific instrumentation. Ultrasound technology has become an essential tool in modern science and engineering because it enables non-invasive measurement, imaging, and inspection. It is widely used in medicine, industrial testing, underwater exploration, and automation systems. In this presentation, we will discuss the physics behind ultrasound waves, the instrumentation used to generate and detect them, and several important real-world applications. To begin, let us introduce ourselves.
Ultrasound refers to sound wave with frequency above 20 kHz, which is beyond the range of human hearing. Like ordinary sound, ultrasound is a mechanical wave that requires a medium for propagation. It travels through materials by creating alternating compressions and refraction of particles. Because ultrasound has a much higher frequency than audible sound, it can provide detailed measurements and images of internal structures. To understand why ultrasound is so useful in scientific instrumentation, we first need to examine its fundamental wave properties.
The behavior of ultrasound wave is governed by the relationship between velocity, frequency, and wavelength. As frequency increases, wavelength decreases. This shorter wavelength allows ultrasound systems to detect smaller objects and produce higher resolution image. However, higher frequencies also experience greater energy loss during propagation, reducing penetration depth. Therefore, engineers must balance image resolution and penetration when designing ultrasound systems. Now that we understand the basic wave properties, we can explore how ultrasound waves are generated and detected. We can also use V equal to F lambda to calculate wave velocity.
Okay, the generation and detection of ultrasound wave rely on the piezoelectric effect. Certain materials such as lead zirconate titanate or PZT can convert electrical energy into mechanical vibration and vice versa. When an alternating voltage is applied, the crystal vibrates and produces ultrasound wave. When reflect wave return, the crystal convert those vibration back into electrical signal. This ability to act as both a transmitter and receiver make piezoelectric materials ideal for ultrasound instrumentation. After generation, this wave must travel through different materials and their behavior depends strongly on the properties of the medium.
Now, let's take a look on ultrasound propagation in materials. The speed and behavior of ultrasound wave depend on the physical properties of the medium, particularly density and elasticity. Generally, sound travels faster in solid than in liquids and gases because particles are more closely packed and can transfer energy more efficiently. For example, ultrasound travel much faster in steel than in water or air. Understanding wave propagation is important because it influences how ultrasound signals interact with different materials. Moreover, wave velocity can be defined as V is equal to square root of E over rho, where V is a wave velocity in a unit of meter per second, E shown as elastic modulus and rho shown as density. One important property that describes this interaction is acoustic impedance.
Acoustic impedance is defined as the product of a material's density and sound velocity. It represents how much resistance a material offers to the propagation of sound wave. Different materials have different acoustic impedance value. When ultrasound travels between two materials with different impedances, part of the wave is reflected while the remainder is transmitted. This principle is fundamental to many ultrasound applications, especially medical imaging and industrial inspection. To understand this process further, we need to examine wave reflection and transmission.
When an ultrasound wave encounters a boundary between two materials, part of its energy is reflected and the other part is transmitted. The amount of reflected energy depends on the difference in acoustic impedance between the two materials. We can use R equal to load impedance minus characteristic impedance of the transmission line over load impedance plus characteristic impedance of the transmission line power of 2. A larger impedance difference produces stronger reflections, which can be detected and analyzed by ultrasound instruments. These reflections form the basis of image formation and defect detection. Besides reflection, ultrasound wave may also experience other effects during propagation.
Okay. As ultrasound waves travel through a medium, their intensity gradually decreases due to attenuation. Attenuation occurs because of absorption, scattering, and reflection loss. Refraction may also occur when waves enter a new medium at an angle, causing a change in direction. Scattering happens when ultrasound interacts with a small particle or irregular structures. Understanding this effect is essential because they directly influence measurement accuracy and image quality. Next, we will look at the component of a complete ultrasound instrumentation system.
Now, let's talk about ultrasound instrumentation system. A typical ultrasound instrumentation system consists of several key components. These include a pulse generator, transducer, receiver amplifier, signal processor, and display unit. The pulse generator excites the transducer, which produces ultrasound wave. Reflected signals are then received, amplified, processed, and displayed as useful information. The effectiveness of the system depends not only on hardware but also on how the signals are processed. This brings us to signal processing techniques.
Signal processing plays a crucial role in converting raw ultrasonic signals into meaningful data. One common technique is the time of flight method, which measures the travel time of ultrasound wave to determine distance. Other techniques include filtering, beamforming, fast Fourier transform analysis, and digital image reconstruction. These methods improve measurement accuracy, reduce noise, and enhance image quality. With the instrumentation fundamentals covered, we can now explore major applications of ultrasound technology.
One of the most well-known applications of ultrasound is medical imaging. Ultrasound scanners create images by transmitting sound waves into the body and analyzing the returning echoes. This technique is widely used in obstetrics, cardiology, and abdominal examination. Unlike X-rays, ultrasound does not use ionizing radiation, making it safer for repeated examinations. Another important medical application involves measuring blood flow using the Doppler effect.
Okay, Doppler ultrasound is based on the Doppler effect which occur when sound waves are reflected from moving object. In medical application, moving red blood cell cause a frequency shift in the reflect ultrasound signal. Okay, for the Doppler equation is FD equal to 2F naught V cos theta over C. By measuring this shift, the velocity and direction of blood flow can be determined. This technique is commonly used to assess cardiovascular health and detect circulatory disorders. Beyond medicines, ultrasound is also widely used for industrial inspection.
Non-destructive testing or NDT uses ultrasound to inspect materials without causing damage. Ultrasonic pulses are transmitted into a material and reflections from cracks, voids, or defects are analyzed. This method is commonly used in aircraft structures, pipelines, wells, and power plants. The ability to identify internal defects while preserving the material makes ultrasound a valuable industrial tool. Another important industrial application is flow measurement.
Ultrasonic flow meters measure the velocity of fluids using ultrasound wave. The transit time method compares the travel time of sound wave moving with and against the flow direction. The Doppler method measures frequency shift. caused by particles moving within the fluid. Because these systems are non-invasive and do not obstruct flow, they are widely used in water treatment facilities, oil pipelines, and chemical processing industries. Ultrasound is also important in underwater applications through sonar technology.
Sonar stands for Sound Navigation and Ranging. It operates by transmitting sound pulses into water and measuring the time taken for echoes to return from underwater objects. Using time-of-flight calculations, the distance to the target can be determined. Sonar is widely used for underwater mapping, navigation, fish detection, and submarine tracking. In addition to large-scale applications, ultrasound is also used in sensors and research laboratories.
Okay, ultrasonic sensors provide non-contact measurement of distance, position, and object detection. These sensors are commonly used in robotics, automation system, and manufacturing processes. In research laboratories, ultrasound can be used for material characterization, particle analysis, and acoustic measurement. Their ability to provide rapid and accurate measurement make them valuable scientific instruments. Despite this advantage, ultrasound technology also has several limitations.
Now, let's talk about advantages and limitations. Ultrasound technology offers many advantages, including non-invasive operation, real-time measurements, safety, and relatively low cost. However, it also has limitations. High frequency wave experience significant attenuation, limiting penetration depth. Image quality also can be affected by noise, scattering, and operator experience. Understanding both the strengths and limitations of ultrasound is important for selecting the most suitable technique for specific applications. Researchers continue to develop new technologies to overcome these challenges.
Recent developments are expanding the capabilities of ultrasound technology. Examples include artificial intelligence assisted image analysis, three-dimensional and four-dimensional imaging, MEMS-based transducers, and high-intensity focused ultrasounds. Researchers are also exploring hybrid technologies such as photoacoustic imaging, which combines optical and ultrasonic methods. These innovations aim to improve resolution, automation, and diagnostic accuracy. Before concluding, let us briefly evaluate the overall significance of ultrasound technology.
Ultrasound remains one of the most versatile technologies in scientific instrumentation. Its success comes from the combination of fundamental wave physics, efficient transducer technology, and advanced signal processing techniques. Compared with many alternative methods, ultrasound offers an excellent balance between safety, cost, accuracy, and real-time operations. However, continued improvements are needed to address limitations such as attenuation and image artifacts.
Okay, in conclusion, ultrasound technology is found on important physics concepts such as wave propagation, piezoelectricity, acoustic impedance, reflection, and Doppler effects. These principles enable a wide range of applications including medical imaging, non-destructive testing, sonar system, flow measurement, and scientific research instrumentation. Its ability to provide non-invasive and real-time information has made ultrasound as indispensable technology in modern science and engineering. As technology continues to advance, ultrasound is expected to play an even greater role in future scientific and industrial development. Thank you for your attention. We welcome any question.